um Hello guys. um Welcome to Control Systems and 6. This video is on root locus, so I'm going to do these two papers. I will show you the difference where you are given a root locus diagram like this one with a point there, with a point there, and another one where you are given the diagram with no point. You can see there's no any point there, so you should know the difference. So let's start with the easy one where you have a point, but first we have to label few things. For example, on your root locus you should know certain things. Let me open the formula sheet on the side so that we can see the formulas we're going to use for this type of a question. The main formula is the K0 formula, which is the sensitivity constant. Yeah, then that's the only formula. The rest is they depend. The rest is on your measurement. It's how you measure. Okay. Yeah. So this is the formula you are going to use, especially on these two formulas. It's not one. What's happening here? Okay. This network is responding slow. Okay, but it's here. So we are going to use these formulas, these two formulas. So for K0 we have delta P1, delta P2, delta Z1, delta. So this delta is the distance from your pole or your zero to the point given. So if you don't have a point, you will need a point. You'll see when we do that type of question. So for example, on this question, you can see I have pole 1 here, I have pole 2 here. So remember the question, where is it? The question paper is divided by delta Z. So every time if I don't have any 0, you are going to take this as 1, not as 0, because when we divide by 0 we're gonna get undefined. So you take it as 1 as per the textbook describes, because there are a lot of questions where you don't have a 0, but sometimes you do have a 0. But if you don't have a 0, you take it as 1, but you always have poles, so there's no question where you want to have a pole. So in this instance where I don't have a 0, I'll take it as 1. So my delta P1 will be the distance from P1 to this point. We are going to measure it. The distance from P2 to this point will be delta P2. This one will be delta P1. Now there's other things you have to know. Remember, this is a 0 point. How do you confirm? You can see horizontally this is a 0 line, vertically this is a 0 line. Always confirm here, because sometimes this pole is not at 0. It's not always at 0. Now there are a few things you have to know in terms of frequencies. The distance from here to here, this is the same as damped frequency always. Now, and the distance from your 0 to the P1 is the undamped natural frequency. Don't forget those two, undamped natural frequency. Now the angle of inclination between your undamped natural frequency line and this, it's the theta. It's the same theta you are going to use to calculate the damping ratio or the damping factor there, cos theta. So you need to measure that angle and calculate the cos theta. So usually guys, with students, I say you can use a protractor to get the angles, but I prefer you use the algebraic method where you use your Pythagoras method. For example, if I want Wn, I know I can say this is 3, then going upwards this is 6, because you can see this block is 3 3. You see, so if you use a ruler, for instance, you might find out from here to here is 1 centimeter, and you might forget that 1 centimeter is equals to 3 units, so it's better to just use algebraic form. So if I'm looking for Wn, I'll just say what? I'll say 3 squared plus 6 squared under the square root, right? The hypotenuse. Even for the angle, you're going to use tan to get the angle on the side. You don't have to do it on the answer sheet. You can do it on the side. You say tan opposite over adjacent, you get the angle. Then now you come substitute the angle. You say cos of that angle, because they mark that step where you say cos of the angle, they mark the angle, then you get the answer. Yeah, but use algebraic to because sometimes even these drawings are not drawn up to scale, so the measurement with rulers can be inconsistent, but this method is always fine, right? So yeah, so just remember these two. So usually they say the distance to P1 is equals to Wn, but you will notice it's not always. It's only if the pole is at 0. Sometimes the pole is not at 0. Most of the questions the pole is at 0, but sometimes it's not at 0, so confirm first. But your Wn, it's always from 0 to this. It's not from the pole to this. No, it's always from 0. So now let's get started and see what are they looking for. Okay, I think I should open this twice also, like we did with other questions. Which paper is this? 2023, so that I don't have to. Oh, sorry, I think I opened the wrong paper. I think this one must be open from here. Let me just. Okay guys, so this is question 5 from the question paper corresponding to this diagram, this one. So let's see what the first question what they want. The first question, they say identify your poles. Remember poles, how do you identify poles from the diagram? You identify them with X. Poles, you'll see them with X, and zeros you'll see them with a circular 0. So we don't have zeros, if you remember. We have poles. We have the first pole at 0. We have another pole at, this is 3, 6, 9, 12. Minus 12. You can, I'm not guessing, they are given here at the bottom. You see? That's minus 12. So when you identify your poles, you can just come here. This is question 5.1. Let me reduce the thickness. So I'll say 5.1 poles equals to 0 and minus 12. That's the first one. Now number 2, calculate the sensitivity constant. Remember the formula for sensitivity constant? We discussed it when we started. Since I have, you should notice the formula at the top, it says delta P1, delta P2, then it says up to infinity. So if I have only 2 poles, I'll end at P2. If I have 3 poles, I'll add P3. Then because I don't have any zeros, I'll just say delta Z1. I don't have to say Z1, Z2 because I don't have anyone, right? Then don't forget this one, I'm going to take it as 1. Then these 2, I'm going to measure them. How do we measure them? Remember I said you don't have to use a ruler, you can use Pythagoras. The delta P1 is this distance here. The Pythagoras of that triangle is what? It's like this. I have 6 vertical, I have 3. So we know how to do that, right? You do 3 squared, 6 squared. You see, I'm doing it on the side, I'm not doing it on the answer sheet, because on the answer sheet they expect you to use the ruler and get the answer. So let's do it. So I have 3 squared and 6 squared. So I'm gonna have, and always round off your answer to one decimal place because you are using a ruler, remember. So I'll say 6,7. So my answer for that will be 6,7 times delta P2. Let's see the distance to P2. If we do the P2 triangle, I'm sure we can all agree. If I draw it here, the vertical is still the same 6. What about the horizontal? I have 3, 6, 9 from here to here, because now our triangle ends here, right? So this is 9. So we know how to do that. 6 squared plus 9 squared. What do we get? 6 squared plus 9 squared. Sorry. Plus 9 squared. So I'm getting 10.8. So I just say 10.8. Then I'm gonna put that in the calculator. 6.7 times 10.8. I don't have to put divide by 1 because we know it's not there. So my answer is 72.36. That one you can write it as is because we did not measure that one, we calculated that one. See, that's how you calculate your sensitivity constant. Now number 3. Guys, remember, if you don't understand, you can just pause, go back. I don't have to re-explain this, it's a video. Okay, number 3, what do they want? WD, the damped resonant frequency. I said, and the next one they want undamped, so they want WDWN. Remember from this, I said the damped is always the vertical to the point. Then the undamped is from 0 to WN. So in this case, my damped, which is vertical, it's 6. But remember, this is frequency, so you put frequency units. What about undamped? Undamped, we saw from the diagram, it's exactly like P1. But it's not always like P1. It's only like P1 if your first pole is at 0, it's at origin, which would be 6.7. Remember, we calculated that. Now 5.5. What could they want? Damping factor. How do we get damping factor? It's cos theta. So we need the angle first. So you're going to come here and say damping factor from the formula sheet is cos theta. So you must say cos of what angle? They want you to measure the angle, but remember guys, I said these things are not drawn to scale. So this angle, this triangle is this one. So you are going to use tan method to get that angle. So we know tan is opposite of adjacent. So arctan of opposite to the angle at 6/3. So if I say arctan of 6/3, and make sure you calculate it on degrees, because I know when we are in N6 we do maths and radians, we do other things and radians, so just make sure you are on degrees. So we have what, 63. You don't have to say 63.4, you can just say 63 because you're using a protractor. Remember, say 63. See, that's my angle, the angle I'm going to use here, cos 63. This what's wrong with this? Okay, my pen responds to network, so if it's bad, my pen also doesn't write well. Yeah, so that's my answer there. I'll say cos 63. So for writing cos 63, there's a mark because they expect you to have got the angle. I don't know if it's network or it's my calculator. Okay, cos 63, which is, your damping factor is always less than 1, so which is 0.454. You can write it like that because we didn't measure that, we calculated that. 454, just like that. Do we have another question? Yes. At which frequency does the system become unstable? So guys, with this one I'll explain it to you quickly. So now I'm going to erase these things. You can just rewind the video and check these things again, or write them on your notes so that I can explain nicely. Okay, others don't wait. So you see, this line is called the root lock. This line, it's the one when we did the root locus, where we drew it, we have this asymptote line, which is also a root lock. So you can call it a locky or a system, doesn't matter, you can put. So now the only time this system will be unstable is if this line will ever cross the JW axis, the imaginary axis. So looking at this line is going vertically upwards and vertically down, so it will never cross this line. So your answer will be the system will never be unstable because your root loci does not cross the JW axis. That's your answer. So sometimes you have questions like this. So sometimes you'll get a system like this. Then they will give you that line like this. Then let's say here they say it's 4 and here it's -4. Same thing. If they ask you at which point, which frequency does this system becomes unstable, you check where it crosses the JW axis. So now you can say the frequency where it becomes unstable is 4 rad per second. But if it looks like it will never cross, you say it will never be unstable because it will never cross your JW axis. That's all. Even if we go to this other question, you see this is round like this. There's no way it looks like it's going to cross the JW axis. So this on this system you will have the same answer. It will never be unstable because it will never cross this. But sometimes you'll get the one I just drew for you here. Where did I draw? Here, where it crosses. So you must remember, when it becomes only unstable if it crosses this axis, the JW axis. That's all guys, we are done. Let's go to the next paper, this one. Let me open the question paper for that quick. Okay guys, question 5 again. I say you have a root locus plotted, which is this one. And then they say use the root locus to plot. Use the root locus plot to determine open loop poles and zeros, because now we have poles and zeros, right? So we know how to identify poles and how to identify zeros, right? So this one I think is the 2022 paper, August 2022. The other one we did was 2023, August or April, just confirm. So they want poles and zeros, so we have to check on the diagram. So let's check. We can see I have P1 here, I have P1 here, I have P2 here, I have Z1 here. So let's see, this is P1 is at 0, P2 is between 2 and -3, which is -2.5. Z1 is at -4. So we see 0, -2.5 for poles. Z is at -4. That's first question. Now Number 2. The smallest value of the damping ratio that the system could have. Remember last time we needed the damping ratio because we know the formula for damping ratio is cos theta. We needed an angle. How did we get an angle? We had a point that we were measuring an angle from 0 to that point. In this case we don't have a point, so how are you going to do it? You are going to use every time you don't have a point, you're going to create a point. The point should be a line from this and a tangent. We know a tangent, if I draw a line, you can use a ruler. If you use a ruler, you must get a straight a line touching this circle once. That's your point. I don't know if I have any straight line here I can use. I don't think so. What am I gonna do? Okay, let me just okay guys, I was checking if I have a ruler here. No. Let me see, what is this? It looks like I don't have any ruler there, so let me check this one lastly. Let me check what do I have here. Nothing. Okay guys, but with you guys are going to use a ruler, but with me, let's say, because I wanted the line, so I'll draw a tangent. I'll draw a tangent. Okay, I'll use blocks. You see these blocks? I'll go to the center of this block. Oh, but it doesn't have to be the center because we are drawing at the tangent, remember? So you just play around with the ruler and check where it meets, where it touches the graph at one point. So for example, your ruler, you can't put it like this. It touches 2 points. You see, it's not a tangent. That's wrong. So you must make sure it touches 1 point. So for me, let's say it was like this, because I don't have a ruler. I'll just assume. So it looks like I'll touch my point somewhere there, somewhere here with me, right? Then that can be a point. Now if I have a point like this, it's like the previous question we did. Now we have everything. I can see my WD will be here. Then from this distance to this point it's Wn, and it's also delta P1. From this pole 1 to this point, we know it's what? It's delta P2. And from 0, it's just that I didn't draw accurate, so you guys must do it accurately and check the memos, check if you're getting the same answer. For me, obviously I won't get with the memo unless if I was spot on with the tangent, because that line doesn't look straight. That's delta Z1, right? So now let's check. Now we can calculate. Remember the question, they wanted K0. What's the formula for K0? I don't know why. Okay, formula for K0 we know. We have 2 poles, so I'll just put 2 poles. I have 1 set. So now I won't put 1 here, I'll put an extra number because we have a 0, right? So let's calculate. Let's start with our first pole here. So if we draw the triangle, remember it's that one where we must do the triangle. So here we will just assume, because we can't use a ruler. You can use a ruler if you want, but the answers will be. So let's start with the triangle to Z1. So let's say this point is A. So our Z1 will look something like this, right? So the distance from here to A, remember here it's 2,5. So that looks like it's closer to 3. So I can say 2,8 or 2,7. I'll say it's 2,8 here. Then the vertical, I can say it's 2,2, because we can say here it's 2. It's not far from that. We can say it's 2,2, like that. Then now, how do we calculate this? 2 comma 2 squared plus 2 comma 8 for z1. What will we get? Square root 2 comma 2 comma 8. I'm getting 5 comma 3 comma 6 if I round it off. So I'll say the first one is 3 comma 6. The second one, if we draw, this one will be a very small triangle. It will be something like this. So if P1 here is at 2 comma 5, and remember A, we said it's 2 comma 8, so which means the difference is what? 0.3. The vertical for all of them is the same, is 2 comma 2. How do we calculate that? 0 comma 3 and 2 comma 2. I hate it when the calculator is slow. See, now I removed my plus. Eish. Yeah, this calculator is slowing me down. Okay, then what do we get? Come on. We get 2 comma 2 also, because yeah, maybe they are on the same length. It's just that the way I drew the tangent, remember? But it's fine, you take it as 2 comma 2. Now the distance to z1, if we draw the triangle for z1, it will be like this, right? Don't forget this doesn't change, the vertical is the same. Now if z1 is at minus 4, we know from minus 4 to here it's 1 unit. Then if this is 2 comma 8, then the difference here will be only 2, so that will be 1 comma 2. Hope you understand, because remember we are not going to, we are going here, which is, we said from here to here it's 1.8. It's 0.8, I mean. Yeah, I'm sure you get it, just make sense of it, please. So we agreed that's 1 comma 2. So okay, not 1 comma 2, sorry, we still have to calculate it. Okay, let me calculate it, I'll come back. So we just change that 1.3, 0.3 to 1 comma 2. Why do I always erase the plus? So what do we get? We get 2 comma 5. So that's what I'll put there, 2 comma 5. Then now we can calculate our K0 quick. 2 comma 6, 2 comma 2. Okay, let me confirm. Comma 6, yeah, but I could sense that something is not fine. This calculator wants to make my video long-ish. 3 comma 6, 2 comma 2, 2 comma 9. Yeah, that looks fine. So I'm getting 3 comma 17 or 168. Just like that. Now let's go to the next question. Oh, I think I jumped something. Oh yeah, that's a mistake, guys. The first question, they were not looking for K0, they were looking for the damping ratio. So which means K0 is 5.5. So we did 5.5 before everything. So they were looking for damping ratio, which is cos theta, but we still needed that. We needed that 0.4. Where's the diagram for the angle. So which means I can use this first triangle to get the angle. How do we get that angle? We use arctan opposite over adjacent. Because we said this 2,8, 2,2. Remember the angle is always from 0 to our point. So let's do it quick. Arctan of 2,2. It's important to read the question. 2.8. Okay, I'm getting 38. I'll just say 38. Remember, you are supposed to measure that angle. So this is cos 38 degrees. Now you put that in the calculator, because they're going to give you 1 mark for the angle and 1 mark for the answer. It says 0.788. See, now we can move to the next question, number 3, where they want, I'm sure the frequencies now, they want the WD, then the next one they want WN. We know WD is the vertical, we already did it on our triangles, it's 2,2, right? WN will be the same as delta P1, because it's from 0, P1 is at 0. So yeah, so we have WD at 2,2 rad per second. We have WN at 3,6, if you remember here, rad per second. Then 5.5 we did it, it's K0. Then the last question is probably the frequency at which the system becomes unstable. We know the system will never be unstable because this line here doesn't look like it will go this side and cross the GW. So you just say the system will never be unstable because it will not cross the JW axis. That's